When we discussed how wavelet convolution works, you learned that we can conceptualize wavelet convolution, or when we implement wavelet convolution as multiplication in the frequency domain, that allows us to conceptualize wavelet convolution as a process of bandpass filtering the data. And in particular, what we do is take the frequency characteristics of the wavelet and pass through the frequency characteristics of the EEG data, and that gives us our bandpass filtered signal. And of course, we don't just use real valued wavelets, we use complex valued wavelets, and this allows us to extract power and phase information from the result of convolution. So this is one mechanism of filtering, or this is one approach to filtering. And in this lecture, I'm going to introduce you to another method of filtering, which is FIR bandpass filtering. So we can think about three different ways of filtering data, or three different types of filters. One is called a low-pass filter. And here the idea, so it's called low-pass because we are allowing the low frequencies to pass through the filter. And then there is a high-pass filter where we are allowing the high frequencies to pass through the filter while attenuating or eliminating the lower frequency characteristics. And of course, the third type of filter is the bandpass, or the narrow band filter, which you already know. This is implemented, or so far we've learned how to implement a narrow band filter through wavelet convolution. And today we're going to learn a different method of implementing a narrow band filter. So you might wonder why, I guess I should say, low pass filters and high pass filters are great, of course, but they're not terribly useful for time frequency analyses. And that's because in time frequency analyses, what we're generally interested in is concentrating the energy at one particular frequency, or isolating the energy of one particular frequency. So low pass and high pass filters are generally not very useful. We really just want to use bandpass filters for doing time frequency analyses. So you might wonder what's wrong with wavelet convolution, and why do we need any other type of bandpass filtering? I think the main answer to this question that provides the motivation for the filter-Hilbert method is because wavelets always have a Gaussian shape in the frequency domain, with a peak in the shape at the frequency corresponding to the sine wave of the wavelet. So having a Gaussian in the frequency domain is very nice. Using wavelet convolution guarantees that you will always have a smooth filter shape in the frequency domain. You're never going to have any sharp edges. This is important for avoiding edge artifacts, which I'll discuss in a few minutes. But the fact that the Morley wavelet is always a Gaussian in the frequency domain can actually also be a limitation in some situations. And so imagine you are interested in the gamma band, but let's say the sort of broad gamma band, like 30 to 80 hertz. If you wanted to measure activity at 30 to 80 hertz with Morley wavelets, what you would have to do is construct a bunch of wavelets and convolve the data with a bunch of wavelets between 30 and 80 hertz. So here I have an illustration of the frequency domain representations of 20 wavelets between 30 and 80 hertz. So if you really just had a very focused hypothesis on the 30 to 80 hertz range, you would need to use all these wavelets, and you would need to sort of have a loop that goes over frequencies and run wavelet convolution 20 times, and then average all of these results together. And you can see that when you're doing this averaging, of course the result will be dominated by 30 to 80 hertz, but you'll have quite some contribution from dynamics lower than 30 hertz, and also quite some contribution from frequencies above 80 hertz. And so this is not really a very optimal approach. Wouldn't it be nice if we could have one filter that would span from 30 to 80 hertz? So it turns out you are never going to achieve this with the wavelet. You can never parameterize a wavelet such that you get one wavelet that nicely covers 30 to 80 hertz without too much influence of frequencies below 30 hertz or above 80 hertz. And so this is really, I think, the primary motivation for using FIR filtering in time frequency analyses in neuroscience. The advantage of FIR filters, as I'll show you in a few minutes, is that you are not limited or constrained to a particular shape in the frequency domain. Instead, you can define the filter to have whatever frequency domain shape you want it to have. And so this is really unlike wavelet convolution, where, as I just mentioned, the shape is always a Gaussian no matter what. So here you can see we have a kind of plateau-shaped filter, and this one has a center frequency of 20 hertz. But of course, you could sort of move this up and create one filter that would have a plateau shape function that would go from 30 hertz to 80 hertz. And this is really the primary motivation for using FIR filters and the filter-Hilbert method more generally in neuroscience time frequency analyses. Okay, so how do you create this filter? I guess I should say, in theory, you can create this filter to have whatever shape you want. It can be kind of a weird shape filter. You can have multiple frequency peaks in the filter, but these are generally something you want to avoid because you are not going to, or Matlab is not going to be able to construct a really good, high quality filter kernel in the time domain that corresponds to any arbitrary mapping in the frequency domain. So in practice, you want your FIR filters always to have a plateau shape in the frequency domain. And the way you do this, I'll explain it a little bit, I'll give you the overview now, and then we'll see this in Matlab in a minute. The way you do this is by defining a so-called ideal filter that has 6 points. Although in fact you only really define 4 of these points. The first point is DC, that's 0 frequency. The last point is the Nyquist frequency. And these other 4 points, these are the things that you have control over. So points 3 and 4, these would be the edges of your filter. And then points 2 and 5 are the transition, or define the transition zones from these frequency edges that you care about down to 0. And so you might think that the best filter would be a perfect edge here. So you stop at exactly 80 hertz, for example. But it turns out that having really sharp edges like this in the frequency shape of your filter is not really ideal. In fact, it can cause some problems and produce some artifacts in the time domain reconstructions. Here's the reason why. Let's imagine a perfect edge in the frequency domain. So here we have a frequency domain signal where it's all zeros and it's just ones here at this one particular frequency. So you can see this is a very sharp edge. It's a sharp edge on both sides. In fact, it's just an impulse response. So now the question is, what is the time domain representation of this frequency response? Well, I'm sure you already guessed the answer. The time domain representation of this response, so if we take the inverse Fourier transform of this, we get a sine wave. It's a pure sine wave. And so we can actually think about a sine wave as being a reflection of an edge artifact in the frequency domain. So this is kind of an interesting alternative way to think about sine waves as being artifacts of edges in frequency domains. And so when you have a perfect sine wave, you can think of this as just being a really horrible edge artifact of a perfect edge in the frequency domain. Of course, well, I guess it's not fair to call this an artifact per se, but we can say that this is a feature of having a sharp edge in the frequency domain. And so now going back to the filter, if you would have a perfect edge here in your filter, what's going to happen in the time domain reconstruction you're going to get a pure sine wave back in the data, which is not something you want. You want the filter to best reflect the characteristics of the actual data, and not some edge artifacts that are produced by having very straight edges in the frequency domain. So this is one advantage of Morley wavelet convolution, that you never have to worry about these kinds of transition zones, because you know that the shape in the frequency domain will never have any sharp edges. Nonetheless, this is a feature that we have to work with in order to have the freedom to define any kind of plateau-shaped filter that we want for any width of frequencies. Okay, so let's take a look at this in Matlab. So here in this first cell, what we're going to do is define the Nyquist frequency, define the filter bounds. So we're going to create a filter that goes from 4 Hertz to 10 Hertz. The transition width here, I define it as a fraction of the frequency. So the lower transition width is going to be 0.2 times 4, and the higher zone is going to be 0.2 times 10. Here we define the filter order, and the filter order defines the length of the filter in the time domain. I will show you a little bit more later what the implications of this filter order are for the shape of the filter that you can reconstruct. In general, so you can play around with this parameter, and there are ways to set this parameter to optimize the frequency characteristics, but the kind of standard default response filter order, without really having to think too much about it, is to use 3 times the ratio of the sampling rate to the lower edge of the frequency bound. But this number 3, this is not a magic number. Later on we'll set it higher, and we'll see that we get even better frequency precision. Okay, and then here we define, here's the ideal response. This is the amplitude of the ideal response. So this would be, from what I showed you in the PowerPoint slide, this would be 0, and this would be the Nyquist frequency. Here are the upper edges, and these zeros here define the transition width. These are the actual frequencies, and I think it's easier just to show you in a plot. So here in this first plot, I'm plotting the ideal response as a function of the frequencies here. So these frequencies here, now this is a vector of frequencies, but this is not in Hertz, this is in a fraction of the Nyquist frequency. So you can see how we're defining these. It's 0 at the beginning and the Nyquist frequency at the end. And then the 2 points in the middle are the bounds of the frequency range that we want. And then the point before this is the transition width times the frequency bound. So this is going to give us 0.025 in normalized units. And now you can see when we multiply this by the Nyquist, it ends up being 3.2 Hertz. And then after the upper bound of the filter that we want, we get to the transition width plus the upper bound, or times the upper bound, and that gives us 12 Hertz. So this is the frequency characteristics of our ideal filter, and this is what the time domain representation looks like. And now here I use the Matlab function called filtFilt. This does zero phase shift filter, so it filters the data forwards in the time domain. This forward time filtering actually induces some phase shifts, and so then the data are flipped around backwards and filtered again backwards in time, which doesn't change the frequency characteristics because the data have already been filtered, but it reverses the phase offset that's introduced by the forward filtering, which is also sometimes called causal filtering. And then here I plot the filtered data from one channel. And actually, I just now noticed that this is a different channel from what I'm plotting here. So this should really be, let's try this at 47. Yeah, that looks better. So now you see the raw data. This is the ERP from channel 47. And now in red, you see the bandpass filtered signal. from 4 to 10 hertz, which is using this filter kernel that's defined by this frequency response. Okay. So now that brings us back to this slide which I showed in the previous lecture on the Hilbert transform. And here now you know that you can go from raw EEG data. You can apply complex Morley wavelet convolution, or you can apply the Hilbert transform after bandpass filtering the EEG data. Both of these will give you the so-called analytic signal, from which you can extract the projection onto the real axis, which is the bandpass filtered signal, the distance from the origin of this complex space to each of these complex points, and you square this and you get the power, and you get the angle of this vector relative to the positive real axis, and then you get the phase angle time series. I'm sorry if you're bored with me repeating this over and over again, but I think it's an important point, so it's worth repeating. In the previous lecture, I showed you how the Hilbert transform works, and I also showed you that applying the Hilbert transform to broadband data is technically valid, it's accurate, but it provides results that are extremely difficult to interpret because they're basically just dominated at every time point by whatever frequency happens to have the largest power in the signal. And EEG data are very dynamic, and they're very and they have broadband characteristics. And so what you really want to do is apply the Hilbert transform after already applying some kind of narrowband filter. You can use FIR filtering the way I just showed you, or you can use any other kind of filters, IIR filters, or any other kind of filters, anything that's will constrain the frequency characteristics of the data to be in a relatively small range. That's what you want to do before applying the Hilbert transform. The last thing I want to discuss is a little bit about parameterization of filters. So these types of plateau-shaped bandpass filters have several parameters, but one of them is the width of the frequency response in the frequency domain, and this provides the same time-frequency trade-off that we saw with wavelet convolution and the number of cycles when creating the Morley wavelets. So here, for example, I'm showing two different filters. This one is 4 hertz width. They're both centered at 20 hertz, 4 hertz width and 20 hertz width. And you can see that the 4 hertz width filter obviously has much higher frequency precision. So you'll be more certain that the dynamics you're measuring with this filter really are driven by 20 hertz. And the 20 hertz width filter is much wider, so that frequency precision is much lower. However, when you go back to the time domain, you look at the time domain kernels that are associated with these bandpass filters. You can see that you can't see it so easily in this plot, which is why I showed the envelope of the kernels over here. So now you can see the filter that has the better frequency precision also has the worse time precision, and vice versa. The broader the frequency is, the broader the kernel is in frequency domain, the more narrow it is in the time domain. So here we see the trade-off between temporal precision and frequency precision in FIR filtering. So I'd like to illustrate this to you, actually not exactly the way I showed with the width of the filter, but with the width of the transition zone. And so here what we're going to do is create 3 different filters that have the same band range, so from 7 hertz to 12 hertz. And the widths will differ, so 10% or 15% or 20%. And basically this parameter defines the gentleness of the roll-off characteristics of the filter. So this, with 20%, this is going to be the most gentle filter. It's going to include energy from more frequencies below 7 hertz and above 12 hertz, but we can also be more confident that there's not going to be any ripple artifacts coming back into the time domain, and therefore the time frequency domain, representation of the signal. Okay, so here we see the filter kernel in the time domain and the frequency domain. There are some subtle differences, and I'll get back to these in a minute, but you can see they generally look fairly similar. So despite these three different parameters, the filter kernels look fairly similar. And you can also see that this kernel doesn't really look very much like a plateau, like a flat top plateau, like what I showed in the lecture. I'm going to get back to this in a minute. We can change a parameter in the filter setup and make this filter kernel have a more plateau-like shape. But first I want to show what happens when you apply each of these filters to data. And so here I'm just applying the filter to the data, and then here applying the Hilbert transform. So now we're going to do the full filter-Hilbert method. From the result of the Hilbert transform, we can extract power, which is the magnitude squared. And then we're averaging over trials, and then here I'm computing decibel normalization. So in fact, a lot of this code is really similar to what you've seen before with the wavelet convolution. And the main new functions are, filt, and I didn't talk about these dynamics, the details of the implementation too much with this function fi, or least squares, but you can read more about it in the book. All right, so here we see data. These are data from electrode 01, and we see the time frequency power for these three different filters. You can see in general the results are really similar for these three parameters, right? So the main features of the data are present for all of them. There are two more kind of minor features that are noticeable here. One is that the energy or the power seems to be higher for the filter with the wider transition zone compared to the middle transition zone compared to the smallest transition zone. So it always goes, blue, red, yellow. And this should not be too surprising because the wider filter actually is covering more frequencies. So there's more energy at more frequencies that are contributing to the signal. And so therefore it's not that surprising that the overall power is a little bit higher. The second thing you can notice is that the temporal precision appears to be a little bit better with the higher transition width of the filter. So you can see the 20% filter, or 20%, the filter with the 20% transition widths compared to the filter with the 10% transition width. The larger filter transition width data, the decay is faster, and then you also see the shouldering process here, which you don't really see with the more narrow filter. And this is exactly the time frequency precision trade-off that you see. So here we get more temporal information with the wider filter, but we include some additional frequencies below 7 and above 12 hertz. Now maybe you think that this is introducing a bias across these three different filters, and in some sense, yes. So there is a bias that is introduced, but of course in practice you don't compare these different filter characteristics. You pick one set of filter parameters and you apply them evenly and sort of fairly to all of the conditions, all of the trials, all the electrodes, all of your subjects, all of your groups, whatever. And so any of these biases that are affecting the nature of the information that you can extract out of the data are affecting all of your data in the same way. So these biases are not going to influence your condition comparisons, for example. All right, so I want to get back briefly to this issue here, the filter kernel not being very plateau-like. So here we have the, if you remember from the lectures on the Fourier transform, that in order to increase the resolution in the frequency domain, what we want is to have more points in the time domain. And so if we want this to look more like a plateau, basically we just need higher frequency precision, and we can do this by having more points in the time domain. And so now what I'm going to do is change the filter order, leave everything else the same, change the filter order from 3 times this ratio. And remember I said that this 3 is not a magic number, it's kind of an arbitrary number. And we can set this to 8. And now I think I'll also change the figure, so I'll make this figure 6 so we can compare. And now you see, comparing figure 4 to figure 6, that this frequency response now is much more of a plateau-like shape. And you can also see that the filter kernel in the time domain is much longer. So this is actually not surprising. This was the parameter that I changed, is the length of the filter. But what that did was give us this gave us the opportunity to have a more plateau-like shape in the frequency domain. Okay, so now let's see what the effect is going to be on the data. So I'll also change the figure number here. Now you see, comparing figure 7 to figure 5, the results really don't change a huge amount. So they do change some, of course. And in fact, the main change is that now we have slightly better temporal precision. So we can see some more, slightly more dynamics here than we could see here. But the results overall don't really differ that much. And this leads me to the final point that I want to say, which is perhaps the most important point. And that is that all of these analyses have different parameters and settings that are associated with them. And there's really no kind of a priori way to know what is going to be the best or the optimal parameter for all situations and all frequencies and all electrodes and all subjects and so on. And so I think any real results in your data should be robust to these fairly minor changes in filter characteristics and filter settings. For example, if you see some results, some difference between condition A and condition B, when you set it to the filter order to be 5 versus 3, then if that is the only thing that makes you have a significant difference or not, then I would say you really don't have a real effect. Then it's just some quirky little feature that one filter setting happened to pick up. So I think what you should be looking for in your data are features that are robust to a reasonable range of parameters. And so there's never going to be a single optimal point in this very large parameter space for exactly how you need to construct your filters. And I mention this here because in the psychology ERP world, there's quite some very stringent vocal opinions about exactly what characteristics your filters should have. I take a slightly more relaxed and perhaps holistic view. I think if you have a real finding in your data, it will be robust to a reasonable range of parameters. And so these are the kinds of findings that you want to be focusing on. I don't think you should feel comfortable publishing a finding that you get with this parameter and not with this parameter. So needless to say, there are quite a few parameters of FIR bandpass filtering. And so this is the primary reason why, in general, I prefer using Morley wavelet convolution for time frequency analyses rather than FIR filtering. FIR filtering, I think, is great and it's very powerful in some situations when you really have a good motivation for focusing on some frequency band and you want to maximize the amount of control that you have over that frequency band. But I would say these are more the exceptions than the rule. And so in most cases, you probably want to stick to Morley wavelet convolution because you know that the Morley wavelets always have a Gaussian shape in the frequency domain. They're simply easier to construct, easier to control, and it's harder to go wrong with wavelet convolution compared to FIR bandpass filtering. Okay, so the world of digital filtering and FIR filters and IR filters, this is a really big world, and a lot of engineers and mathematicians really focus a lot of time and energy on on all the ins and outs and the fine details of these filters. This lecture I gave is really like barely scratching the surface of all the details of bandpass filtering. But I wanted to keep it short intentionally because I think unless you have a specific reason, you should generally prefer to use Morley wavelets for time-frequency decomposition in neuroscience. So that does it for this lecture, and see you in the next lecture.